The barber paradox. Can logic shave it clean? Imagine a small town with one peculiar rule. The town's barber shaves all and only those who do not shave themselves. But here's the twist. Who shaves the barber? If the barber shaves himself, he can't because he only shaves those who don't shave themselves. If he doesn't shave himself, he must because he shaves everyone who doesn't shave themselves. A logical deadlock. This paradox, sparked by Bertrand Russell, isn't just a quirky brain teaser. It reveals deep problems with self-reference and set theory. Can you spot where the logic unravels? Or is this a... The liar paradox is a well-known logical paradox that arises when considering statements that refer to themselves in a way that creates a contradiction. The classic form of the paradox involves a statement such as, "This statement is false." Let's analyze why this is paradoxical. 1. If the statement is true, if this statement is false is true, then what it says must be the case. But the statement claims that it is false, which would mean it is not true. This is a contradiction. 2. If the statement is false, if this statement is false, then what it says is not true. But if it is not true that the statement is false, then the statement must be true. Again, this leads to a contradiction. In both cases, we end up with a contradiction, making it impossible to consistently assign a truth value, true or false, to the statement. This self-referential loop creates the paradox. Historical context. The liar paradox has been discussed since ancient times, with early references in Greek philosophy. It is often attributed to the ancient Greek philosopher Epimenides, who is said to have stated, "All Cretans are liars," while himself being a Cretan. However, this formulation is not strictly paradoxical unless it is interpreted self-referentially. Implications. The liar paradox has significant implications for logic, philosophy, and linguistics. It challenges classical notions of truth and falsity, particularly in systems that rely on binary truth values, true or false. It also raises questions about self-reference and the limits of language and logic. Attempts to resolve the paradox. Various solutions have been proposed to address the liar paradox, including 1. Hierarchical solutions. Some philosophers, like Alfred Tarski, have suggested that truth predicates, like is true or is false, must be organized in a hierarchy to avoid self-reference. In this view, a statement at one level can only refer to statements at lower levels, preventing paradoxical loops. 2. Non-classical logics. Alternative logical systems, such as paraconsistent logic or dialetheism, allow for contradictions to exist without collapsing the entire system. In these frameworks, a statement can be both true and false, or neither, without leading to logical chaos. 3. Rejecting self-reference. Some approaches argue that self-referential statements are meaningless or ill-formed and should be excluded from logical analysis. Despite these efforts, the liar paradox remains a topic of debate and continues to inspire new ideas in the study of logic and language. It serves as a reminder of the complexities and limitations inherent in systems of reasoning. Zeno's paradox of Achilles and the tortoise *** is one of the most famous paradoxes in ancient Greek philosophy. It was formulated by the pre-Socratic philosopher Zeno of Elea, circa 490–430 BCE, to challenge our understanding of motion, infinity, and continuity. The paradox is part of a series of paradoxes Zeno created to support the ideas of his teacher, Parmenides, who argued that motion and change are illusions. The paradox. The paradox goes like this. 1. Setup. Achilles, the fastest runner in Greek mythology, races against a tortoise. The tortoise is given a head start. 2. The argument. By the time Achilles reaches the point where the tortoise started, the tortoise will have moved a little farther ahead. By the time Achilles reaches that new point, the tortoise will have moved again, albeit a smaller distance. This process continues indefinitely, with Achilles always needing to reach the tortoise's previous position, while the tortoise keeps moving forward. 3. Conclusion. Zeno argues that Achilles can never overtake the tortoise because he must always cover an infinite number of smaller and smaller distances to catch up. Why it's paradoxical. At first glance, the paradox seems to suggest that motion is impossible or that Achilles can never pass the tortoise, which contradicts our everyday experience. The paradox relies on the idea of dividing time and space into an infinite number of smaller intervals, creating an infinite regress that appears to make motion impossible. Key concepts. 1. Infinite divisibility. Zeno's paradox assumes that space and time can be divided infinitely. This leads to the idea that Achilles must complete an infinite number of tasks, reaching each successive point where the tortoise was, in a finite amount of time. 2. Convergent series. Modern mathematics, particularly calculus, provides a resolution to the paradox. The distances Achilles must cover form an infinite series, but this series converges to a finite sum. For example, if the tortoise has a 100-meter head start and Achilles runs 10 times faster, the distances Achilles must cover form the series. 100 plus 10 plus 1 plus 0, 0.1 plus 0, 0.0, 1 plus those dots. This is a geometric series that sums to a finite value, approximately 111.11 meters, meaning Achilles will overtake the tortoise in a finite amount of time. 3. Limits and calculus. The paradox is resolved by understanding that an infinite number of steps can be completed in a finite time if the steps become smaller and smaller. This is a fundamental concept in calculus, where limits are used to handle infinite processes. Philosophical implications. Zeno's paradoxes, including Achilles and the tortoise, challenge our understanding of space, time, and infinity. They raise questions about the nature of motion and whether it is continuous or discrete, the concept of infinity and whether it can be completed, the relationship between mathematics and physical reality. Resolution. While Zeno's paradoxes were originally intended to argue against the reality of motion, modern mathematics and physics provide tools to resolve them. The key insight is that infinite processes can have finite outcomes, and motion is possible even in a universe where space and time are infinitely divisible. In summary, Zeno's Achilles and the tortoise paradox is a profound exploration of the nature of motion and infinity. While it seems paradoxical at first, it is resolved by understanding the mathematics of infinite series and the concept of limits. It remains a valuable thought experiment for exploring the foundations of mathematics and physics. The unexpected hanging paradox is a fascinating thought experiment that challenges our understanding of knowledge, prediction, and surprise. Let's explore it without focusing on symbolic or mathematical contexts, and instead delve into its philosophical and logical implications in a more intuitive way. The story. A prisoner is sentenced to be hanged, but the judge adds a twist. The hanging will occur sometime next week, Monday through Friday, and it will be a surprise. The prisoner will not know the day of the hanging until the executioner arrives at his cell on that day. The prisoner, confident in his reasoning, tries to figure out when the hanging will occur. He thinks, 1. Friday. If I'm still alive by Thursday evening, the hanging must be on Friday. But then it wouldn't be a surprise. So Friday is ruled out. 2. Thursday. If I'm still alive by Wednesday evening, the hanging must be on Thursday. But since Friday is already ruled out, it wouldn't be a surprise. So Thursday is ruled out. 3. He continues this reasoning, ruling out Wednesday, Tuesday, and finally Monday. 4th. Conclusion. The hanging cannot occur on any day without violating the condition that it must be a surprise. But then the executioner arrives on, say, Wednesday, and the hanging is indeed a surprise. This contradicts the prisoner's reasoning. So, why it's paradoxical? The paradox lies in the tension between the prisoner's logical reasoning and the actual outcome. The prisoner believes he has logically eliminated all possibilities, yet the executioner proves him wrong. The judge's condition that the hanging must be a surprise seems impossible to fulfill, yet it happens. This creates a loop of contradiction. The prisoner's reasoning undermines the very possibility of the hanging being a surprise, yet the hanging occurs in a way that defies his reasoning. Key philosophical questions. 1. What does it mean for something to be a surprise? The paradox challenges our understanding of surprise. Can an event be both logically predictable and genuinely surprising? The prisoner's reasoning assumes that if he can predict the hanging, it cannot be a surprise. But the executioner's actions show that surprise can still occur, even in the face of logical reasoning. 2. The limits of human knowledge and prediction. The prisoner's reasoning assumes perfect foresight, but in reality, our knowledge is often incomplete or uncertain. The paradox highlights the gap between logical reasoning and real-world unpredictability. 3. Self-reference and circular reasoning. The prisoner's reasoning is self-referential. He tries to predict the executioner's actions based on his own predictions. This creates a loop where the prisoner's logic undermines itself, leading to a contradiction. 1. Real-world analogies. The paradox mirrors situations in life where we try to predict the unpredictable. Stock market. Investors try to predict market movements, but unexpected events often defy their predictions. Weather forecasting. Meteorologists use models to predict the weather, but surprises still happen. Personal decisions. We often plan for the future, but life can throw unexpected events our way. In each case, the paradox reminds us that logic and prediction have limits, and surprise is an inherent part of life. Why it matters. The unexpected hanging paradox isn't just a clever puzzle. It has deeper implications. It challenges our confidence in logical reasoning and highlights the complexity of human knowledge. It raises questions about free will and determinism. Can we truly predict the actions of others, or are there always elements of unpredictability? It serves as a reminder that life is full of uncertainties, and no amount of reasoning can fully eliminate the possibility of surprise. Conclusion. The unexpected hanging paradox is a thought-provoking exploration of logic, knowledge, and surprise. While the prisoner's reasoning seems sound, it ultimately fails to account for the unpredictability of the executioner's actions. This paradox reminds us that life is often more complex than our logical models, and surprises can defy even the most careful reasoning. It's a timeless reminder to embrace uncertainty and recognize the limits of human understanding. The ship of Theseus is a classic paradox in philosophy that explores the nature of identity and continuity. The paradox is named after the mythical ship belonging to Theseus, the founder king of Athens. The central question it raises is whether an object that has had all of its components replaced remains fundamentally the same object. The paradox. 1. Original scenario. Imagine the ship of Theseus is kept in a harbor as a museum piece. Over time, its planks decay and are replaced one by one with new, identical planks. 2. Question. After all the planks have been replaced, is it still the same ship of Theseus? 3. Extended scenario. If someone collected all the original planks and reassembled them into a ship, would that reassembled ship be the true ship of Theseus? Philosophical implications. Identity over time. The paradox challenges our understanding of identity and whether it is based on material composition, form, or something else. Continuity versus replacement. It questions whether gradual change preserves identity, even if all original components are eventually replaced. Essentialism versus nominalism. The paradox touches on whether objects have an essential identity that persists despite changes, essentialism, or whether identity is merely a label we assign based on certain criteria, nominalism. Variations and thought experiments. Theseus's ship and the replacement, paradox. If all parts are replaced, is it still the same ship? The reassembled ship. If the original parts are reassembled, is that the original ship? The gradual replacement, paradox. If parts are replaced gradually, at what point does the ship cease to be the original? Philosophical perspectives. 1. Heraclitus. The ancient philosopher Heraclitus argued that you cannot step into the same river twice, emphasizing constant change and flux. This aligns with the idea that the ship of Theseus is not the same after its parts are replaced. 2. Plato and essentialism. Plato's theory of forms suggests that there is an ideal, unchanging form of the ship of Theseus, which remains the same regardless of material changes. 3. John Locke. Locke's theory of personal identity, which focuses on continuity of consciousness, can be analogously applied to objects. He might argue that the ship remains the same as long as there is a continuous existence and form. 4th. Thomas Hobbes. Hobbes extended the paradox by considering whether the reassembled original planks would constitute the original ship, adding complexity to the debate. Modern interpretations. Psychological continuity. Some modern philosophers apply concepts of psychological continuity to objects, suggesting that identity is maintained through a continuous existence and function. 4-dimensionalism. This view treats objects as extended in time as well as space, suggesting that the ship of Theseus at different times are temporal parts of a larger, 4-dimensional object. Conclusion. The ship of Theseus paradox remains a compelling thought experiment that challenges our understanding of identity, continuity, and change. It has no definitive answer, but serves as a valuable tool for exploring deep philosophical questions about the nature of existence and identity. The crocodile paradox is a classic logical paradox that dates back to ancient Greek philosophy. It is a self-referential problem that challenges our understanding of truth, promises, and logical consistency. Here's an explanation of the paradox and its implications. The paradox. A crocodile steals a child and promises the parent, "If you correctly predict what I will do with your child, I will return the child. If you do not predict correctly, I will eat the child." The parent responds, "You will eat my child." This creates a paradox. 1. If the crocodile eats the child, the parent's prediction was correct, so the crocodile must return the child. 2. If the crocodile returns the child, the parent's prediction was incorrect, so the crocodile must eat the child. The crocodile is trapped in a logical loop and cannot act without breaking its own promise. Key elements of the paradox. 1. Self-reference. The paradox arises because the parent statement refers back to the crocodile's action, creating a loop of dependency. 2. Logical consistency. The crocodile's promise creates a situation where no action, eating or returning the child, can satisfy both the promise and the parent's prediction. 3. Truth and falsity. The paradox challenges the binary nature of truth and falsity, as neither outcome, eating or returning, resolves the contradiction. Now, philosophical implications. 1. Nature of promises. The paradox highlights the complexities of making and fulfilling promises, especially when they involve self-referential conditions. 2. Logical loops. It demonstrates how self-referential statements can lead to logical inconsistencies, similar to the liar paradox. This statement is false. 3-point decision theory. The paradox raises questions about how to make decisions in situations where the outcome depends on predicting one's own actions. 4th, truth and deception. It explores the boundaries of truth and deception, as the crocodile's promise is inherently deceptive or impossible to fulfill. Possible resolutions. 1. Rejecting the premise. One could argue that the crocodile's promise is inherently flawed or impossible to fulfill, rendering the paradox meaningless. Introducing a third option. The crocodile could choose a third action, e.g., releasing the child without eating or returning it, to break the loop. 3. Temporal separation. The crocodile could delay its decision, creating a separation between the prediction and the action, though this doesn't fully resolve the paradox. Accepting the paradox. Some philosophers argue that the paradox is unsolvable and serves as a reminder of the limitations of logic and language. Connection to other paradoxes. The crocodile paradox is closely related to other self-referential paradoxes, such as the liar paradox. A statement like, "This sentence is false," creates a similar loop of contradiction. The barber paradox. A barber who shaves all and only those who do not shave themselves cannot logically exist. Conclusion. The crocodile paradox is a fascinating exploration of logic, language, and the limits of truth. It challenges us to think critically about self-referential statements and the nature of promises, and it remains a valuable tool for understanding the complexities of logical reasoning. While it may not have a definitive resolution, it continues to inspire philosophical debate and reflection. The grandfather paradox is a classic time travel paradox that explores the logical inconsistencies and consequences of changing the past. It is one of the most well-known thought experiments in discussions about time travel and causality. Here's a detailed explanation of the paradox and its implications. The paradox. The grandfather paradox is formulated as follows. Imagine a time traveler goes back in time to a point before their grandfather had children. The time traveler kills their grandfather or otherwise prevents their grandfather from meeting their grandmother. As a result, the time traveler's parent, and consequently, the time traveler themselves, would never be born. If the time traveler is never born, they could not have gone back in time to kill their grandfather. But if the grandfather was not killed, the time traveler would exist and could go back in time to kill their grandfather. This creates a logical loop. The time traveler's existence depends on their grandfather surviving, but their actions in the past would prevent their own existence. Key questions raised. 1. Causality. Can the past be changed, or is it fixed? If the past is changed, what happens to the future? 2. Consistency. How can the universe maintain logical consistency if a time traveler's actions create a contradiction? 3. Existence. Does the time traveler cease to exist if they alter the past in a way that prevents their own birth? Philosophical and scientific implications. The grandfather paradox touches on fundamental questions about time, causality, and the nature of reality. It has been widely discussed in both philosophy and theoretical physics, particularly in the context of time travel theories. Proposed resolutions. Several theories have been proposed to resolve or address the grandfather paradox. 1. Self-consistency principle, Novikov self-consistency principle. Proposed by Russian physicist Igor Novikov, this principle suggests that any actions taken by a time traveler in the past were always part of history. In this view, the time traveler cannot change the past in a way that creates a paradox. For example, the time traveler might fail to kill their grandfather, or their actions might inadvertently ensure their own existence. This principle maintains a single, consistent timeline where events are self-consistent. 2. Multiple timelines, parallel universes, or branching timelines. This theory, often associated with the many worlds interpretation of quantum mechanics, suggests that any change to the past creates a new parallel timeline. In this scenario, the time traveler kills their grandfather in a new timeline, preventing their own existence in that timeline. However, the original timeline, where the time traveler was born, remains unaffected. This avoids the paradox by allowing multiple, coexisting realities. 3. Predestination paradox. In this view, the time traveler's actions in the past were always part of history and contribute to the events that lead to their own existence. For example, the time traveler might go back in time and inadvertently cause their grandparents to meet, ensuring their own birth. This creates a closed loop where the past and future are interconnected and self-consistent. 4. Impossibility of changing the past. Some theories argue that the past is fixed and cannot be changed. Any attempt to alter the past would fail, either because time travel itself is impossible or because the universe enforces consistency. In this view, the grandfather paradox is a logical proof that time travel to the past cannot occur. 5. Temporal protection hypothesis. Proposed by physicist Stephen Hawking, this hypothesis suggests that the laws of physics prevent time travel to the past in order to avoid paradoxes. Hawking argued that the absence of time travelers from the future is evidence that time travel is impossible. Connection to other paradoxes. The grandfather paradox is related to other time travel paradoxes, such as the bootstrap paradox. An object or piece of information is sent back in time and becomes its own origin, creating a loop with no clear beginning. The Hitler paradox, a variation of the grandfather paradox, where a time traveler goes back in time to kill a historical figure like Hitler, raising similar questions about causality and consequences. Conclusion: the grandfather paradox remains a fascinating and unresolved problem in discussions about time travel. It challenges our understanding of causality, free will, and the nature of time itself. While various theories attempt to resolve the paradox, none have been universally accepted, and the paradox continues to inspire debate in both philosophy and science. Ultimately, it serves as a reminder of the complexities and mysteries of time and existence. The sorties paradox, also known as the paradox of the heap, is a classic paradox in philosophy that challenges our understanding of vague predicates, boundaries, and categorization. It is named after the Greek word sorties, meaning heap, and was first formulated by the ancient Greek philosopher Eubulides of Miletus. The paradox highlights the difficulties in defining clear boundaries for concepts that are inherently vague. The paradox. The paradox is typically presented as follows. 1. Premise. 1. A single grain of sand does not make a heap. Second. Premise. 2. Adding one grain of sand to something that is not a heap does not turn it into a heap. 3. Conclusion. By repeated applications of premise 2, no number of grains of sand can ever make a heap. This leads to a contradiction because we know that, in practice, a large number of grains of sand do form a heap. The paradox arises from the vagueness of the term heap and the inability to define a precise threshold at which a collection of grains becomes a heap. Now, alas, key features of the paradox. 1. Vagueness. The term heap is vague. It lacks a clear, definitive boundary. 2. Small increments. The paradox relies on small, incremental changes, adding one grain of sand at a time, that seem insignificant individually, but collectively lead to a significant change. 3. Inductive reasoning. The paradox uses inductive reasoning, where a general rule is applied repeatedly, leading to an absurd conclusion. Schrödinger's philosophical implications. The sorties paradox raises important questions about language, logic, and the nature of reality. 1. Vagueness in language. Many terms in natural language, e.g., tall, bald, rich, are vague. The paradox challenges how we define and use such terms. 2. Boundaries and thresholds. It questions whether there are sharp boundaries between categories or whether such boundaries are inherently fuzzy. 3-point logic and reasoning. The paradox challenges classical logic, which assumes that statements are either true or false, with no middle ground. It suggests that some statements may be indeterminate or require a different logical framework. Proposed solutions. Philosophers and logicians have proposed various solutions to address the sorties paradox. Here are some of the most prominent ones. 1. Epistemicism. This view holds that vague predicates do have sharp boundaries, but these boundaries are unknowable or unknown to us. For example, there is a specific number of grains of sand that constitutes a heap, but we cannot determine what that number is. 2. Many-valued logic, fuzzy logic. This approach introduces degrees of truth, allowing statements to be partially true or false. For example, a collection of grains might be 70% a heap, with the degree increasing as more grains are added. 3. Supervaluationism. This theory suggests that vague statements can be evaluated as true, false, or indeterminate, depending on how the vague term is precisified. For example, a collection of grains might be considered a heap under some precisifications, but not under others. 4. Contextualism. This view argues that the meaning of vague terms depends on the context in which they are used. For example, what counts as a heap might vary depending on the situation or the speaker's intentions. 5. Rejecting classical logic. Some philosophers argue that classical logic is inadequate for dealing with vagueness and propose alternative logical systems, such as paraconsistent logic or dialetheism, which allow for contradictions or true contradictions. Applications and relevance. The Sorties paradox has implications beyond philosophy, influencing fields such as 1. Linguistics. It informs debates about the nature of meaning and the use of vague language. 2. Artificial intelligence. It raises challenges for AI systems that rely on precise definitions and classifications. 3. Law and ethics. It highlights difficulties in applying vague legal or ethical standards, e.g., reasonable doubt or fairness. Connection to other paradoxes. The Sorties paradox is related to other paradoxes that involve vagueness or gradual change, such as the bald man paradox. Removing one hair at a time from a man with a full head of hair does not make him bald, but at some point he becomes bald. The paradox of the ship of Theseus. Gradual replacement of parts raises questions about identity and continuity. Conclusion. The Sorties paradox is a profound and enduring challenge to our understanding of language, logic, and categorization. It demonstrates the difficulties of dealing with vagueness and the limitations of classical logic in handling gradual change. While various solutions have been proposed, none have fully resolved the paradox, and it continues to inspire debate and reflect. The omnipotence paradox is a classic philosophical and theological problem that questions the nature of unlimited power, particularly in the context of an omnipotent being such as God. The paradox arises when considering whether an all-powerful being can perform tasks that seem logically impossible or self-contradictory. The most famous formulation of the paradox involves the question: can an omnipotent being create a task that it cannot accomplish? The paradox. The paradox is often framed as follows. 1. Premise: an omnipotent being can do anything. 2. Question: can an omnipotent being create a stone so heavy that it cannot lift it? If the being can create such a stone, then there is something it cannot do: lift the stone, which means it is not omnipotent. If the being cannot create such a stone, then there is something it cannot do: create the stone, which also means it is not omnipotent. 3. Conclusion. In either case, the being cannot be truly omnipotent. This creates a logical contradiction, challenging the coherence of the concept of omnipotence. Mawaj, key issues raised. 1. Definition of omnipotence. The paradox highlights the difficulty in defining what it means to be all-powerful. Does omnipotence include the ability to perform logically impossible tasks? 2. Logical consistency. It raises questions about whether an omnipotent being is bound by the laws of logic or can transcend them. 3. Nature of power. the paradox explores the limits of power and whether true omnipotence is a coherent concept. Philosophical and theological implications. The omnipotence paradox has been debated for centuries in philosophy and theology, with various thinkers offering solutions or reinterpretations of omnipotence. It touches on fundamental questions about the nature of God, power, and logic. Proposed solutions. Several approaches have been proposed to resolve or address the paradox. 1. Rejecting the paradox as a misunderstanding of omnipotence. Some theologians argue that the paradox is based on a flawed definition of omnipotence. They claim that omnipotence does not include the ability to perform logically impossible tasks, as such tasks are meaningless. For example, Thomas Aquinas argued that God's omnipotence includes the ability to do all that is possible, but not the logically impossible. 2. Reinterpreting omnipotence. Some philosophers suggest redefining omnipotence to mean the ability to do anything that is coherent or non-contradictory. In this view, creating a stone so heavy that an omnipotent being cannot lift it is a self-contradictory task, and therefore not within the scope of omnipotence. 3. Semantic solutions. Some argue that the paradox arises from linguistic confusion or misuse of terms. For example, the phrase, "a stone so heavy that it cannot be lifted," may be inherently meaningless or nonsensical. By clarifying the language, the paradox can be dissolved. 4. Modal approaches. Modal theories of omnipotence focus on the ability to bring about possible states of affairs. In this framework, the paradox does not arise because creating an unliftable stone is not a possible state of affairs. 5. Paradox as a limit of human understanding. Some theologians argue that the paradox reflects the limitations of human language and logic when discussing divine attributes. They suggest that omnipotence is beyond human comprehension and cannot be fully captured by logical paradoxes. Connection to other paradoxes. The omnipotence paradox is related to other philosophical and theological problems, such as the problem of evil. If God is omnipotent, omniscient, and benevolent, why does evil exist? The paradox of the stone. A variation of the omnipotence paradox that specifically focuses on the creation of an unliftable stone. The liar paradox. A self-referential paradox that challenges the coherence of truth and falsity. Tao conclusion. The omnipotence paradox remains a thought-provoking challenge to the concept of unlimited power. It forces us to critically examine the definitions and implications of omnipotence, as well as the limits of logic and language in discussing divine attributes. While various solutions have been proposed, the paradox continues to inspire debate and reflection in philosophy, theology, and beyond. Ultimately, it serves as a reminder of the complexity and mystery inherent in concepts like power, divinity, and existence. The revan paradox, also known as Hempel's paradox or the paradox of confirmation, is a problem in the philosophy of science and inductive reasoning. It was formulated by the German logician Carl Gustav Hempel in the 1940s to illustrate a counterintuitive aspect of the hypothetico-deductive model of scientific confirmation. The paradox arises from the application of Nikod's criterion and the principle of induction to the confirmation of universal statements. Thackeray, the paradox. The paradox is based on the following example. 1. Hypothesis. All ravens are black. This can be formally written as a universal statement. If something is a raven, then it is black. RB 2. Confirmation. According to Nicod's criterion, observing a black raven confirms the hypothesis. 3. Logical equivalence. The statement, all ravens are black, is logically equivalent to its contrapositive. If something is not black, then it is not a raven. Not B implies not R. 4. Counterintuitive result. By the principle of logical equivalence, observing a non-black object that is not a raven, e.g. a green apple, should also confirm the hypothesis. This leads to the paradoxical conclusion that observing a green apple confirms the statement, all ravens are black, which seems counterintuitive and nonsensical. Key issues raised. 1. Confirmation theory. The paradox challenges how we determine what counts as evidence for a scientific hypothesis. 2. Logical equivalence. It highlights the tension between logical equivalence and intuitive notions of evidence. 3. Inductive reasoning. The paradox raises questions about the validity of inductive reasoning and the nature of scientific confirmation. Philosophical implications. The raven paradox has significant implications for the philosophy of science, particularly in understanding how evidence supports or confirms scientific theories. It forces us to reconsider what counts as relevant evidence for a hypothesis. How do we reconcile logical principles with intuitive judgments about evidence? What are the limits of inductive reasoning in science? Proposed solutions. Several approaches have been proposed to resolve or address the raven paradox. 1. Rejecting Nicod's criterion. Some philosophers argue that Nicod's criterion, which states that only observations of instances that satisfy both the antecedent and consequent of a universal statement confirm the hypothesis, is too simplistic and should be revised or rejected. 2. Bayesian confirmation theory. Bayesian approaches to confirmation theory suggest that evidence should be evaluated based on how it affects the probability of a hypothesis. In this framework, observing a black raven increases the probability of the hypothesis. All ravens are black more than observing a non-black non-raven, e.g. a green apple, because ravens are rare compared to non-black objects. 3. Selective confirmation. This approach argues that only observations of ravens, whether black or not, are relevant to confirming the hypothesis, all ravens are black. Observing non-ravens, even if they are not black, is irrelevant because they do not provide information about the color of ravens. 4. Paradox as a misapplication of logic. Some philosophers argue that the paradox arises from a misapplication of logical equivalence in the context of confirmation. They suggest that logical equivalence does not imply evidential equivalence. 5. Contextual relevance. This view emphasizes the importance of context and background knowledge in determining what counts as relevant evidence. For example, in the context of studying ravens, observing a green apple is irrelevant, whereas observing a raven is directly relevant. Connection to other problems. The raven paradox is related to other issues in the philosophy of science and epistemology, such as the problem of induction. How can we justify inductive reasoning, which moves from specific observations to general conclusions? The Grue paradox. A problem raised by Nelson Goodman that challenges the validity of inductive reasoning by introducing artificial predicates like Grue, green before time t, blue after time t. underdetermination of theories by evidence. The idea that multiple theories can be consistent with the same evidence, making it difficult to confirm one theory over another. Conclusion: the Raven paradox is a fascinating and enduring challenge to our understanding of scientific confirmation and inductive reasoning. It highlights the complexities of determining what counts as evidence for a hypothesis and the limitations of purely logical approaches to confirmation. While various solutions have been proposed, the paradox continues to inspire debate and reflection in the philosophy of science, reminding us of the nuanced and often counterintuitive nature of scientific reasoning. The Monty Hall problem is a probability puzzle based on a game show scenario. It is named after Monty Hall, the original host of the television game show Let's Make a Deal. The problem became famous after it was posed in a letter to the American statistician by Steve Selvin in 1975, and later gained widespread attention when Marilyn Vos Savant discussed it in her Parade magazine column in 1990. Despite its seemingly simple setup, the problem often leads to intense debate and confusion because the correct solution is counterintuitive. The problem. The scenario is as follows. 1. You are a contestant on a game show. There are 3 doors: door 1, door 2, and door 3. 2. Behind one door is a car, the prize you want, and behind the other 2 doors are goats. 3. You pick a door, e.g., door 1. The host, who knows what is behind each door, opens one of the remaining 2 doors, e.g., door 3, to reveal a goat. The host then asks you, do you want to switch your choice to the other unopened door, e.g., door 2, or stick with your original choice? 6. The question is, should you switch your choice, stick with your original choice, or does it not matter? The counterintuitive solution. The correct strategy is to always switch, as this gives you a 2/3 chance of winning the car, while sticking with your original choice gives you only a 1/3 chance. Why it's counterintuitive. Many people assume that after one door is revealed, the remaining 2 doors have an equal probability, 1/2, of hiding the car. However, this intuition is incorrect because the host's action of revealing a goat provides additional information that affects the probabilities. That's your explanation of the solution. 1. Initial choice. When you first pick a door, e.g., door 1, there is a 1/3 chance that the car is behind your chosen door and a 2/3 chance that the car is behind one of the other 2 doors. 2. Host's action. The host, who knows what is behind each door, always opens a door that reveals a goat. This action does not change the initial probabilities, but provides additional information. 3. Switching. If you initially picked a goat, which has a 2/3 probability, switching will always lead you to the car. If you initially picked the car, which has a 1/3 probability, switching will lead you to a goat. Probability calculation. Therefore, switching gives you a 2/3 chance of winning the car, while sticking with your original choice gives you only a 1/3 chance. Common misconceptions. 1. Equal probability after revealing a goat. Many people mistakenly believe that after one door is revealed, the remaining 2 doors have an equal probability, 1/2, of hiding the car. This ignores the fact that the host's action is not random, but is based on knowledge of what is behind each door. 2. Independence of events. Some people assume that the host's action is independent of your initial choice, but this is not the case. The host's action is dependent on your initial choice and the location of the car. Mathematical proof. The probabilities can be demonstrated using conditional probability or by enumerating all possible scenarios. Scenario 1. You initially pick the car, 1/3 probability. Host opens a door with a goat. If you switch, you lose. Scenario 2. You initially pick a goat, 2/3 probability. Host opens the only remaining door with a goat. If you switch, you win the car. Thus, switching wins the car in 2 out of 3 scenarios, giving a 2/3 probability of winning. Practical demonstration. To better understand the problem, you can simulate it. 1. Play the game multiple times, always sticking with your initial choice. You will win approximately 1/3 of the time. 2. Play the game multiple times, always switching. You will win approximately 2/3 of the time. Narshranj, connection to other problems. The Monty Hall problem is related to other probability puzzles and paradoxes, such as Bertrand's box, paradox, a problem involving conditional probability and the selection of boxes with different contents. The 2-envelope problem, a paradox involving 2 envelopes with different amounts of money and the expected value of switching. Danihya, conclusion. The Monty Hall problem is a classic example of how probability can be counterintuitive. It demonstrates the importance of carefully considering the information provided and how it affects the probabilities of different outcomes. While the correct solution, always switch, may seem surprising at first, it is firmly grounded in the principles of probability theory. The problem continues to be a valuable teaching tool for understanding conditional probability and decision-making under uncertainty. The teletransportation paradox is a thought experiment that explores the philosophical and ethical questions surrounding identity, consciousness, and continuity in the context of teleportation. It is often associated with the ship of Theseus problem and raises questions about what it means to be the same person after being disassembled and reassembled, or having one's consciousness transferred. The paradox. Imagine a teleportation device that works by scanning your entire body, disassembling it at the atomic level, and then transmitting the information to a distant location where an exact replica is reconstructed. The original you is destroyed in the process. Is the person who emerges at the destination still you? Or are you effectively dead, with the new person being a copy with your memories and personality? Key questions. 1. Continuity of consciousness. If the original body is destroyed, does your consciousness continue in the new body? Or is it a new consciousness that simply believes it is you? 2. Identity. Are you the same person if every atom and memory is replicated exactly? Does identity depend on the physical continuity of your body, or is it tied to the pattern of information that makes up your mind? 3. Ethical implications. If the teleportation process involves destroying the original, is it morally equivalent to killing someone and creating a duplicate? Would you willingly use such a device? Philosophical perspectives. 1. Psychological continuity. View. Some philosophers argue that personal identity is tied to the continuity of memories, personality, and consciousness. From this perspective, the teleported person is still you because they retain your psychological traits. 2. Bodily continuity. View. Others argue that identity is tied to the physical body. If the original body is destroyed, the new person is not truly you, even if they are identical in every other way. 3. Branching identity. Some theories suggest that both the original and the copy could be considered you in some sense, leading to questions about the nature of identity in cases of duplication. Variations of the paradox. Copying without destruction. What if the original is not destroyed? Would there now be two yous? Which one is the real you? Gradual replacement. What if your body is replaced piece by piece over time, as in the ship of Theseus? At what point do you cease to be you? Implications. The paradox has implications for fields like philosophy of mind, ethics, and even practical applications such as cryonics or digital consciousness uploads. It challenges our understanding of selfhood and raises questions about the nature of existence in a world where technology could potentially replicate or transfer consciousness. What do you think? Would you step into a teleportation device if it meant the original you would be destroyed? The twin paradox is a thought experiment in physics that arises from Albert Einstein's theory of special relativity. It explores how time dilation affects two observers moving at different velocities relative to each other. The paradox is called the twin paradox because it typically involves a pair of twins, one of whom travels at a high speed, close to the speed of light, while the other remains on Earth. When the traveling twin returns, they find that less time has passed for them compared to the twin who stayed on Earth. The setup. 1. Two twins. Twin A stays on Earth while Twin B travels in a high-speed spacecraft to a distant star and then returns. 2. High-speed travel. Twin B's spacecraft travels at a significant fraction of the speed of light, causing relativistic effects like time dilation. 3. Time dilation. According to special relativity, time passes more slowly for an object in motion relative to a stationary observer. This means Twin B's clock and biological aging will tick more slowly compared to Twin A's. Minor. The paradox. From Twin A's perspective on Earth, Twin B is moving at high speed, so Twin B's clock should run slower due to time dilation. When Twin B returns, Twin A expects Twin B to be younger. From Twin B's perspective in the spacecraft, Twin A and Earth appears to be moving away at high speed, so Twin A's clock should run slower. Twin B expects Twin A to be younger upon returning. This creates a paradox. Each twin thinks the other should be younger. How can both be correct? Navarro. Resolution. The paradox is resolved by recognizing that the two twins are not in symmetrical situations. Special relativity applies to inertial frames of reference, frames moving at constant velocity, but Twin B's journey involves acceleration and deceleration, changing direction to return to Earth. This breaks the symmetry. 1. Twin A's frame. Twin A remains in an inertial frame, Earth's frame, throughout the experiment. 2. Twin B's frame. Twin B experiences acceleration and deceleration, which means their frame is non-inertial. This asymmetry explains why Twin B ages less. When accounting for the effects of acceleration and the relativity of simultaneity, it becomes clear that Twin B, the traveling twin, will indeed be younger than Twin A when they reunite. Key concepts. 1. Time dilation. Time runs slower for an object in motion relative to a stationary observer. This is described by the Lorentz factor, now in gamma tron frac 1, escort 1, vi2, c2 nargon, where vr is velocity and cr is the speed of light. 2. Relativity of simultaneity. Events that are simultaneous in one frame may not be simultaneous in another frame, moving relative to the first. 3. Non-inertial frames. The traveling twins frame is non-inertial due to acceleration, breaking the symmetry of the situation. Practical implications. The twin paradox is not just a theoretical curiosity, it has real-world implications. For example, GPS satellites must account for time dilation due to their high speeds and weaker gravitational fields, general relativity, to provide accurate positioning data. In science fiction, the paradox is often used to explore the consequences of near light speed travel, such as in stories involving interstellar journeys. Thought experiment. Imagine twin B travels to a star 10 light years away at 80% the speed of light, or v 0.8 c, and from twin A's perspective on Earth, the trip takes our navfrak c 10 1 text light years, 0.8 c, navfrak 10 0.8, or 12.5 years, 12.5 years each way, totaling 25 years. Due to time dilation, twin B experiences less time. Using the Lorentz factor, Mal Arangama, or navfrak 1, esquart naus, the top guide, 2, ha navfrak now 3 no. Twin B's time for the round trip is or navfrak 25 snyan text years, gamma more 15 years. When twin B returns, twin A has aged 25 years, while twin B has aged only 15 years. The twin paradox highlights the fascinating and counterintuitive nature of time and motion in Einstein's theory of relativity. It challenges our everyday understanding of time as a universal constant and demonstrates how motion and gravity can fundamentally alter our experience of reality.
The Sleeping Beauty paradox is a thought experiment in probability and philosophy that explores issues related to self-locating beliefs, conditional probability, and the nature of subjective experience. It was first introduced by philosopher Adam Elga in 2000 and has since sparked significant debate among philosophers, mathematicians, and scientists. The setup: 1. Sleeping Beauty. A participant, often called Sleeping Beauty, is put to sleep on Sunday night. 2. Coin. Flip. A fair coin, 50% heads, 50% tails, is flipped. If the coin lands on heads, Sleeping Beauty is awakened on Monday, and the experiment ends. If the coin lands on tails, Sleeping Beauty is awakened on Monday, put back to sleep, and her memory of the Monday awakening is erased. She is then awakened again on Tuesday, and the experiment ends. 3. Memory erasure. Each time Sleeping Beauty is awakened, she has no memory of previous awakenings during the experiment. 4. Question. When Sleeping Beauty is awakened, without knowing whether it is Monday or Tuesday, what should she believe is the probability that the coin landed on heads? The paradox. The paradox arises because there are two competing answers to the question, each supported by seemingly reasonable arguments. 1. The thirder position. Probability equals 1/3. When Sleeping Beauty wakes up, she considers 3 equally likely possibilities. Heads, and it's Monday. Tails, and it's Monday. Tails, and it's Tuesday. Since only one of these corresponds to heads, the probability of heads is r frac y1 or 3. The Halfer position. Probability equals 1/2. The coin is fair, so the initial probability of heads is 1/2. When Sleeping Beauty wakes up, she gains no new information that would update this probability, so it remains 1/2. Arguments for each position. Thirder argument. The key insight is that Sleeping Beauty's awakening is not independent of the coin toss. If the coin lands on tails, she wakes up twice, Monday and Tuesday, whereas if it lands on heads, she wakes up only once, Monday. From her perspective, there are 3 possible awakenings, each equally likely, and only one corresponds to heads. Thus, the probability of heads is half for argument, the coin is fair, so the probability of heads is 1/2. When Sleeping Beauty wakes up, she does not gain any new information that would change this probability. She knew in advance that she would be awakened at least once, so her awakening does not provide additional evidence about the coin toss. Implications. The paradox raises deep questions about 1. Self-locating beliefs. How should an agent update their beliefs when they are uncertain about their location in time or space? 2-point conditional probability. How should probabilities be updated when the evidence is tied to the number of times an event occurs? 3rd, subjective experience. How does the nature of subjective experience, e.g., memory erasure, affect rational belief? Applications. The Sleeping Beauty paradox has relevance in fields such as probability, theory. It challenges traditional notions of conditional probability and Bayesian updating. Philosophy of mind. It explores the relationship between memory, identity, and belief. Decision. Theory. It has implications for how agents should make decisions in scenarios involving memory loss or repeated experiences. Thought experiment variations. To further explore the paradox, consider these variations. 1. Extreme version. What if the coin lands on tails 99% of the time? Would Sleeping Beauty still believe the probability of heads is 1/2, or would it be much lower? 2. Multiple awakenings. What if the experiment involves more awakenings, e.g., 100 awakenings for tails? How does this affect the probability? 3. No memory erasure. What if Sleeping Beauty retains her memory of previous awakenings? How does this change her belief about the coin toss? Which side are you on? The Sleeping Beauty paradox remains unresolved, with strong arguments on both sides. It challenges our intuitions about probability and belief, making it a fascinating topic for discussion. Do you think Sleeping Beauty should assign a probability of 1/2 or 1/3 to the coin landing on heads? The infinite hotel paradox, also known as Hilbert's paradox of the Grand Hotel, is a thought experiment introduced by the German mathematician David Hilbert to illustrate some of the counterintuitive properties of infinite sets. The paradox demonstrates how an infinite hotel, even when full, can still accommodate additional guests, or even an infinite number of new guests. This paradox is a cornerstone in understanding the nature of infinity in mathematics. The setup. Imagine a hotel with an infinite number of rooms, all of which are occupied. Despite being full, the hotel can still make room for new guests through clever room rearrangements. Key scenarios. 1. Adding 1 new guest. Problem. The hotel is full, but a new guest arrives. How can they be accommodated? Solution. Ask each guest to move to the room with the next number. For example, the guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on. This frees up room 1 for the new guest. Result. The hotel remains full, but the new guest now has a room. 2. Adding an infinite number of new guests. Problem. An infinite number of new guests arrive. How can they all be accommodated? Solution. Ask each current guest to move to the room with a number double their current room number. For example, the guest in room 1 moves to room 2, the guest in room 2 moves to room 4, the guest in room 3 moves to room 6, and so on. This frees up all the odd-numbered rooms, which are infinite in number, for the new guests. Result. The hotel remains full, and all the new guests are accommodated. 3. Adding an infinite number of infinite buses. Problem. An infinite number of buses arrive, each carrying an infinite number of passengers. How can all these passengers be accommodated? Solution. Use a pairing function to map each bus and each passenger to a unique room number. For example, passengers from bus 1 are assigned to rooms using the formula E non-text room 2R1n times 2n 1 non, where n narn is the passenger's seat number. Passengers from bus 2 are assigned to rooms using the formula text room 22 on times 2n 1 arn. Passengers from bus 3 are assigned to rooms using the formula criterion text room 2 more 3 on times 2n 1 enorn, and so on. Result: all passengers from all buses are accommodated and the hotel remains full. Key concepts. 1. Countable infinity. Hilbert's hotel deals with a countably infinite set, meaning its elements can be put into a one-to-one correspondence with the natural numbers 1, 2, 3, 2. One-to-one correspondence. The ability to pair each element of one infinite set with each element of another infinite set without leaving any elements unpaired. 3. Paradoxical nature. The paradox arises because our intuition about finite sets, e.g., a full hotel cannot accommodate more guests, does not apply to infinite sets. Implications. The infinite hotel paradox highlights the strange and counterintuitive properties of infinity. 1. Infinity plus 1 equals infinity. Adding a finite number to infinity does not change its size. 2. Infinity plus infinity equals infinity. Adding two infinite sets together does not change their size. 3. Infinity times infinity equals infinity. Multiplying infinite sets together does not change their size. These properties are fundamental to the study of Hahn transfinite numbers, in set theory pioneered by Georg Cantor. Connection to mathematics. The paradox is closely tied to the concept of cardinality, which measures the size of sets. For example, the set of natural numbers, n, and the set of integers, z, have the same cardinality, even though the integers include more elements, negative numbers. The set of real numbers, \r\, has a higher cardinality than the set of natural numbers, meaning it is more infinite. Thought experiment. Imagine a hotel with an infinite number of rooms, all occupied. Now suppose a guest checks out of room 1. How many rooms are now empty? An infinite number of guests check out of all even-numbered rooms. How many rooms are now empty? In both cases, the hotel remains infinitely full, but the specific arrangement of guests changes. Why does this matter? The infinite hotel paradox is not just a fun mental exercise, it has profound implications for mathematics, physics, and philosophy. In mathematics, it helps us understand the nature of infinite sets and their properties. In physics, it relates to questions about the infinite universe, such as whether space or time is infinite. In a philosophy, it challenges our intuitions about reality and the nature of existence. The infinite hotel paradox is a fascinating exploration of infinity, demonstrating that infinite sets behave in ways that defy our everyday experiences.
The measure problem in cosmology is a fundamental issue that arises when attempting to make predictions in an infinite or extremely large universe. It is particularly relevant in the context of eternal inflation, the multiverse, and the anthropic principle. The problem stems from the difficulty of defining a meaningful probability measure over an infinite set of possible observations or events. Sacker, the core issue. In an infinite universe or multiverse, there are infinitely many occurrences of every possible event. For example, there may be infinitely many planets with intelligent life. There may be infinitely many regions with different physical constants or laws of physics. There may be infinitely many observers with identical experiences. In such a scenario, how do we assign probabilities to events or observations? For instance, what is the probability that we observe a universe with a specific set of physical constants? Without a well-defined measure, probabilities become ill-defined or meaningless. Now, why does this matter? The measure problem is crucial for 1. Cosmological predictions. Making testable predictions about the universe, such as the likelihood of observing certain values for physical constants. 2. Anthropic reasoning. Understanding why we observe a universe that appears fine-tuned for life. 3. Eternal inflation and the multiverse. Interpreting the implications of theories that predict an infinite number of universes with different properties. Chakray. Key challenges. 1. Infinite volumes. In an infinite universe, the number of occurrences of any event is infinite, making it impossible to compare frequencies directly. 2. Dependence on cutoffs. Probabilities often depend on arbitrary choices of how to cut off or limit the infinite volume, leading to inconsistent results. 3. Observer counting. Different ways of counting observers, e.g., by volume, by entropy, by complexity, can yield different probabilities for the same event. Proposed solutions. Several approaches have been proposed to address the measure problem, though none are universally accepted. Here are some of the most prominent ideas. 1. Volume weighting. Assign probabilities based on the volume of space where a particular event occurs. Problem. In an infinite universe, volumes are infinite, making this approach ill-defined without a cutoff. 2. Causal diamond measure. Focus on the finite region of spacetime, causally connected to an observer, the causal diamond. Advantage. Avoids infinities by restricting attention to a finite region. Problem. May not capture all relevant information in a multiverse scenario. 3. Anthropic reasoning. Use the fact that we exist as observers to constrain probabilities. For example, we are more likely to observe a universe compatible with life. Problem. Does not provide a unique measure and relies on subjective assumptions. 4. Stationary measure. Define probabilities based on the rate at which events occur in a given region of spacetime. Advantage. Avoids infinities by focusing on rates rather than totals. Problem. Requires a well-defined notion of time in a multiverse context. 5. Holographic principle. Use the holographic principle to reduce the problem to a finite description on a boundary. Advantage. Provides a finite framework for an otherwise infinite problem. Problem. Still speculative and not fully developed. 6. Bayesian approaches. Use Bayesian probability to update beliefs based on observed data. Advantage. Flexible and can incorporate new information. Problem. Requires a prior probability distribution, which may be arbitrary. Implications for cosmology. The measure problem has profound implications for our understanding of the universe. 1. Fine-tuning. If the universe is infinite, the apparent fine-tuning of physical constants for life may be an illusion, as every possible configuration of constants exists somewhere. 2. Multiverse theories. Theories like eternal inflation and string theory predict a multiverse with an infinite number of universes. The measure problem is critical for interpreting these theories. 3. Observational predictions. Without a solution to the measure problem, it is difficult to make testable predictions about the universe or multiverse. Thought experiment. Imagine an infinite multiverse where every possible universe exists. In some universes, the laws of physics allow for life, while in others, they do not. If you are an observer in this multiverse, what is the probability that you find yourself in a universe compatible with life? How does the answer change if the multiverse is finite versus infinite? Why is it so hard? The measure problem is deeply tied to the nature of infinity and the limits of human intuition. Our everyday experience is based on finite systems where probabilities are well defined. In an infinite universe, these intuitions break down, requiring new mathematical and philosophical tools to make sense of the cosmos. Conclusion: the measure problem remains one of the most challenging and unresolved issues in modern cosmology. It sits at the intersection of physics, mathematics, and philosophy, pushing us to rethink our understanding of probability, infinity, and the nature of reality. Until a satisfactory solution is found, it will continue to be a central topic of debate in the quest to understand the universe. Causal loop paradoxes. Those mind-bending, head-scratching scenarios that make you question everything you thought you knew about time, cause and effect, and maybe even your own sanity. They're like the universe playing a cosmic prank on us, saying, "Oh, you think you understand how things work? Think again." Let's dive into these paradoxes in a way that feels a little more human, a little less like a textbook. What's a causal loop anyway? Imagine you're stuck in one of those annoying loops where you can't figure out what came first, the chicken or the egg. A causal loop is like that, but on steroids. It's when an event in the future causes something in the past, which then causes the future event, and round it goes. It's a closed loop of cause and effect with no clear beginning or end. It's like time itself is trolling you. Now are classic examples to mess with your mind. 1. The bootstrap paradox, aka the where did it come from paradox. Scenario: imagine you find a dusty old book in your attic. It's a masterpiece, full of incredible ideas that change the world. You decide to take it back in time and give it to your younger self, who then publishes it as their own work. Fast forward, and the book ends up in your attic again. The problem: where did the book originally come from? Did it just magically appear out of nowhere? It's like the universe photocopied itself, but no one pressed the print button. 2. The grandfather paradox, aka the oops, I broke time paradox. Scenario: you build a time machine, because why not, and go back in time to meet your grandpa. But instead of a happy reunion, you accidentally prevent him from meeting your grandma. Uh-oh. The problem: if your grandparents never meet, your parents are never born, which means you are never born. But if you were never born, how did you go back in time to mess things up in the first place? Time is giving you a big ol' middle finger here. 3. The ontological paradox, aka the it just exists, okay? Paradox. Scenario: you're a brilliant inventor, and one day, your future self shows up and hands you the blueprints for a time machine. You build it, travel back in time, and give the blueprints to your past self. The problem: who actually invented the time machine? The blueprints just kind of exist with no origin. It's like finding a song on the internet with no artist. It's just there, and you have no idea where it came from. Why does this mess with our brains? Causal loops are so weird because they break the rules of how we think the world works. We're used to cause and effect being a straight line. A causes B, which causes C, and so on. But in a causal loop, A causes B, which causes A, and suddenly the line becomes a circle. It's like trying to figure out who started a rumor when everyone's pointing at everyone else. Can we resolve these paradoxes? Spoiler, it's complicated. People have come up with some clever ideas to try to make sense of these loops, but none of them are perfect. Here are a few. 1. The self-consistency principle. This is the universe's way of saying, "Don't worry, I've got this." The idea is that anytime travel shenanigans have to be consistent with what already happened. So, if you try to go back and stop your grandparents from meeting, something will always get in your way. Maybe you trip and miss your chance, or your grandpa is just really charming and wins your grandma back. The universe won't let you break the timeline. 2. Multiple timelines, aka the parallel universes. Fix. This is the sci-fi favorite. If you go back in time and change something, you don't actually change your past. You just create a new timeline. So, if you stop your grandparents from meeting, you're not erasing yourself. You're just creating a new universe where you don't exist. Your original timeline is safe and sound. Phew. 3. The block universe. Theory, this one's a bit trippy. It says that past, present, and future all exist at the same time, like frames in a movie. If you go back in time, you're just playing out a scene that was always part of the movie. There's no paradox because everything is already set in stone. Free will? What's that? Why are causal loops so fascinating? Causal loops are like the ultimate what-if game. They make us question everything we think we know about time, reality, and our place in the universe. They're also a goldmine for storytellers. Think of movies like Back to the Future, Predestination, or Looper. They're fun to think about because they're so weird and counterintuitive, but they also remind us that the universe is way stranger than we can imagine. A little thought experiment for you. Imagine you're handed a letter. It's from your future self, and it tells you exactly how to build a time machine. You build it, travel back in time, and hand the same letter to your past self. The question is, who wrote the letter? Did it just appear out of thin air? Or is it stuck in an endless loop with no real origin? Final thoughts. Causal loop paradoxes are like the universe's way of keeping us humble. They remind us that there's still so much we don't understand about time, causality, and reality itself. Whether they're resolved through self-consistency, parallel universes, or some other mind-blowing theory, they'll always be a source of wonder and confusion. And honestly, isn't that what makes them so cool? The Connie, two envelopes paradox. A classic brain teaser that seems simple at first, but quickly spirals into a whirlwind of confusion. It's one of those problems where your intuition screams one thing, but logic, or maybe illogic, says something completely different. Let's break it down in a way that feels human, relatable, and maybe even a little fun. The setup. Here's the scenario. 1. You're presented with two envelopes. Let's call them envelope A and envelope B. 2. You're told that one envelope has twice as much money as the other. So, if envelope A has $10, envelope B has either $5 or $20. 3. You pick one envelope, let's say envelope A, but don't open it. Then you're given a choice. Stick with your envelope or switch to the other one. seems straightforward, right? But here's where things get weird. The paradox. You start thinking, maybe I should switch. Let's do the math. 1. Assume envelope. A has xa. If envelope A is the smaller amount, then envelope B has 2x. If envelope A is the larger amount, then envelope B has x plus 2. 2. Calculate the expected value. There's a 50% chance envelope B has $2x and a 50% chance it has x divided by $2. So the expected value of switching is, in our text here, the expected value here, frax are 1, 2 in times 2x, plus our frax in on 2 r, in times 50 whole percent in a fraction na, in our x plus, fraction mar, and fraction mar. This means switching gives you an expected gain of in a fraction war, x on a fraction war, and so you should always switch. 3. But wait, if you switch to envelope B, the same logic applies. Now envelope B has y dollars, and envelope A has either 2y dollars or y half dollars. So switching back to envelope A also seems advantageous. This creates an infinite loop. Switching always seems better, no matter which envelope you're holding. Why is this a paradox? The paradox lies in the fact that the reasoning suggests you should always switch envelopes, which is clearly absurd. If switching is always better, why didn't you just pick the other envelope in the first place? It's like a never-ending game of the grass is always greener on the other side. Where does the logic go wrong? The flaw in the reasoning is subtle but crucial. Here's the problem. 1. Inconsistent use of x. In the calculation, mer xn is used to represent the amount in your chosen envelope, but its value changes depending on whether your envelope is the smaller or larger one. This creates a contradiction because war, x, nen can't simultaneously represent two different values. 2. Correct approach. Let's define the smaller amount as war, y, war. Then the two envelopes contain war, y, war, and war, 2, y, war. If you pick an envelope, there's a 50% chance it has war, y, war, and a 50% chance it has war, 2, y, war. The expected value of your chosen envelope is anio on text 10 expected value. Y on frac y1, 2, and times y plus, on frac y1, y times 2y, 1 frac 1, 3y, y, or if you switch, the expected value of the other envelope is also war, 1 frac 1, 3y, y, 1, nar. So there's no advantage to switching. Why does this mess with our brains? The paradoxy plays on our intuition about probability and expected value. It feels like there's a trick or a hidden advantage, but in reality, the math only works if you're consistent with your definitions. The moment you try to use Rxn in two different ways, the logic falls apart. A simpler way to think about it. Imagine the two envelopes have $10 and $20. If you pick the $10 envelope, switching gets you $20, a gain of $10. If you pick the $20 envelope, switching gets you $10, a loss of $10. On average, switching doesn't give you an advantage. It's a wash. Why is this paradox important? 1. It teaches us about probability. The paradox shows how easy it is to make mistakes when dealing with probabilities, especially when variables aren't clearly defined. 2. It challenges our intuition. Our brains aren't always great at handling abstract problems like this. The paradox forces us to slow down and think carefully. 3. It's fun. Let's be honest. Paradoxes like this are just plain fun to think about. They're like mental puzzles that keep you up at night. A thought experiment. Imagine you're playing this game with a friend. You pick an envelope and your friend picks the other one. Both of you do the expected value calculation and decide to switch. But if switching is always better, how can both of you gain an advantage? It's a classic heads I win, tails you lose situation, but in this case, it's heads I win, tails I also win. Clearly, something's off. Final thoughts. The two envelopes. Paradox is a brilliant example of how something so simple can lead to such deep confusion. It reminds us to question our assumptions, double-check our math, and maybe not always trust our gut when it comes to probability. And hey, if nothing else, it's a great conversation starter. The quantum Zeno effect. A phenomenon so strange and counterintuitive that it feels like it belongs in a sci-fi movie rather than real-life physics. Named after the ancient Greek philosopher Zeno, who famously argued that motion is an illusion. This effect shows how the act of watching something can actually stop it from happening. It's like the universe saying, if a tree falls in the forest and no one is around to hear it, maybe it doesn't fall at all. Let's dive into this mind-bending concept in a way that's, hopefully, easy to grasp. What is the quantum Zeno effect? In simple terms, the quantum Zeno effect is the idea that frequent observation of a quantum system can prevent it from changing. It's as if the universe hits the pause button every time you look at it. This happens because, in the quantum world, observation isn't passive. It actively affects the system being observed. How does it work? Let's break it down step by step. 1. Quantum superposition. In quantum mechanics, particles can exist in multiple states at once. For example, an electron can be in a superposition of spin-up and spin-down states. 2. Wave function collapse. When you measure or observe a quantum system, its wave function, the mathematical description of its state, collapses into one of the possible states. This is why quantum mechanics is so weird. Observation changes the system. 3. Frequent measurements. If you measure a quantum system very quickly and repeatedly, you keep collapsing its wave function back to its initial state before it has a chance to evolve into something else. It's like constantly asking a kid, "Are you asleep yet?" Every time you ask, you wake them up, so they never actually fall asleep. A simple example. Imagine you have a radioactive atom that has a 50% chance of decaying within 1 hour. If you leave it alone, it might decay. But if you check on it every minute, here's what happens. 1. First check. You observe the atom, and it's still intact. The act of observation resets its decay clock. Second check. You observe it again, and it's still intact. The clock resets again. 3. Repeat. If you keep checking frequently enough, the atom never gets a chance to decay. It's like you're freezing it in its initial state. Why is this so weird? The quantum Zeno effect messes with our everyday intuition. In the classical world, watching something doesn't change its behavior. If you watch a pot of water, it will still boil. But in the quantum world, observation is an active process. It changes the system. This effect shows just how different the quantum realm is from our everyday experience. Real-world applications. While it sounds like pure theoretical fun, the quantum Zeno effect has some practical uses. 1. Quantum computing. In quantum computers, qubits, quantum bits, are prone to errors due to decoherence. The Zeno effect can be used to stabilize qubits by repeatedly measuring them, preventing them from drifting into unwanted states. 2. Atomic clocks. The effect can help improve the precision of atomic clocks by stabilizing the atoms used to keep time. 3. Quantum control. Scientists can use the Zeno effect to control the behavior of particles in experiments, essentially freezing them in a desired state. The flip side, the anti-Zeno effect. Just when you thought things couldn't get weirder, there's the anti-Zeno effect. In some cases, frequent measurements can actually speed up the evolution of a quantum system instead of slowing it down. It's like the universe saying, "Oh, you're watching? Let me show off even more." A thought experiment. Imagine you're trying to teach a cat to sit still. Good luck with that. Every time you look at the cat, it freezes in place. If you keep looking at it every few seconds, the cat never moves. But if you look at it in just the right way, maybe it starts moving even faster. That's the Zeno and anti-Zeno effects in action. Just replace the cat with a quantum particle. Why does this matter? The quantum Zeno effect isn't just a quirky curiosity. It has deep implications for our understanding of reality. 1. The role of the observer. It highlights how observation isn't passive in quantum mechanics. The observer plays an active role in shaping the system's behavior. The nature of time. The effect challenges our understanding of how time works in the quantum world. Can time be frozen by observation? What does that even mean? Third, philosophical questions. It raises questions about the nature of reality. If observation can change a system, does reality exist independently of the observer? Final thoughts. The quantum Zeno effect is a perfect example of why quantum mechanics is so fascinating and so frustrating. It's a realm where the rules of common sense don't apply, and where something as simple as looking can have profound consequences. Whether you're the free will paradox, a philosophical and scientific conundrum that has puzzled thinkers for centuries. It's the kind of problem that makes you question everything you think you know about yourself, your choices, and the nature of reality. At its core, the paradox revolves around the tension between free will, the idea that we have control over our actions, and determinism, the idea that everything is predetermined by prior causes. Let's unpack this in a way that feels human, relatable, and maybe even a little existential. What is the free will paradox? The paradox arises when we try to reconcile two seemingly incompatible ideas. 1. Free will, the belief that we have the ability to make choices that are not entirely determined by prior events or external forces. 2. Determinism, the belief that every event, including human actions, is determined by preceding events and the laws of nature. The paradox is this: if determinism is true, then everything we do is the inevitable result of prior causes, and free will is an illusion. But if free will is real, then determinism must be false, and the universe is not entirely governed by cause and effect. So, which is it? Do we have free will, or are we just puppets on the strings of fate? The scientific perspective. Modern science, particularly physics and neuroscience, adds fuel to the fire of this paradox. 1. Physics and determinism. Classical physics, think Newton, suggests that the universe is like a giant clockwork machine. If you know the state of the universe at one time, you can predict its state at any future time. This implies determinism. Quantum mechanics complicates things. At the quantum level, events are probabilistic, not deterministic. But does this randomness give us free will, or is it just another form of unpredictability? 2. Neuroscience and the brain. Studies show that our brains make decisions before we're consciously aware of them. For example, brain scans can predict a person's choice seconds before they feel like they've made it. This raises the question, are our decisions truly free, or are they just the result of unconscious brain processes? The philosophical debate. Philosophers have been wrestling with the free will paradox for centuries. Here are some key perspectives. 1. Compatibilism. This view argues that free will and determinism can coexist. Even if our actions are determined by prior causes, we can still have free will if our actions align with our desires and intentions. Think of it like this. You choose to eat pizza because you like pizza. The fact that your preference for pizza is determined by your biology and experiences doesn't make the choice any less free. 2. Libertarianism, not the political kind. This view insists that free will is real and that determinism is false. It often appeals to the idea of an immaterial soul or mind that can make choices independent of physical causes. The challenge here is explaining how such a non-physical entity could interact with the physical world. 3. Hard determinism. This view accepts determinism and rejects free will. If everything is determined, then our sense of making choices is just an illusion. This can feel pretty bleak. If hard determinism is true, are we just robots following a script? 4th, pessimism, or no free will, now what? Some thinkers, like philosopher Galen Strawson, argue that free will is impossible, even if determinism is false. Why? Because our choices are ultimately shaped by who we are, and we don't choose who we are. Nyar, the moral implications. The free will paradox isn't just an abstract philosophical puzzle, it has real-world consequences. 1. Responsibility. If we don't have free will, can we hold people morally responsible for their actions? If a criminal's behavior is determined by their genes and environment, should we punish them or try to rehabilitate them? 2. Justice. Our legal systems are built on the assumption of free will. If free will is an illusion, does that undermine the foundation of justice? 3. Meaning. If our choices aren't truly free, does life lose its meaning? Or can we find meaning in other ways, even if we're not in control? A thought experiment. Imagine a universe where everything is determined. You're about to make a decision, say, choosing between tea and coffee. Unbeknownst to you, the laws of physics and the state of the universe have already determined your choice. Does it feel like you're making a free choice? If so, does that feeling matter, even if it's an illusion? Why does this matter? The free will paradox forces us to confront some of the deepest questions about who we are and how we fit into the universe. 1. Identity. Are we the authors of our own lives, or are we just characters in a story written by the laws of physics? Agency. Do we have the power to shape our future, or are we just along for the ride? Existence. If free will is an illusion, what does that mean for our sense of self and purpose? Final thoughts. The free will paradox doesn't have an easy answer, and maybe it doesn't need one. It's a reminder that some questions are meant to be pondered, not solved. Whether you believe in free will, determinism, or something in between, the paradox invites us to reflect on what it means to be human in a vast, mysterious universe. So, the next time you're faced with a choice, tea or coffee, to procrastinate or not to procrastinate, Take a moment to wonder, is this decision truly mine, or is it the inevitable result of a cosmic chain of events? And does it even matter, as long as the coffee tastes good? Ah, the paradox of the criterion, a philosophical puzzle that's as frustrating as it is fascinating. It's one of those problems that makes you feel like you're chasing your own tail, trying to figure out how to figure things out. At its core, the paradox is about knowledge and how we can know anything at all. Let's break it down in a way that's relatable, human, and maybe even a little funny. What is the paradox of the criterion? The paradox goes like this. 1. To know something, you need a criterion, a standard or rule to distinguish between what's true and what's false. 2. But to establish that criterion, you need to know something about what's true and what's false. 3rd, so you're stuck in a loop. You need knowledge to have a criterion, but you need a criterion to have knowledge. In other words, it's like trying to start a car without an engine, or trying to bake a cake without a recipe. You can't get started because you don't have the tools to get started. A simple example. Imagine you're trying to figure out which fruits are sweet. You might say, sweet fruits are the ones that taste sweet. But how do you know what sweet tastes like? You'd need to already know which fruits are sweet to define sweetness in the first place. It's a chicken and egg problem. Checker. Why is this a paradox? The paradox highlights a fundamental problem in epistemology, the study of knowledge. How can we justify our standards for knowledge without already having knowledge? It's like trying to pull yourself up by your own bootstraps. It just doesn't work. Historical context. The paradox dates back to ancient Greek philosophy, particularly the work of Sextus Empiricus, a skeptic who used it to argue that we can't really know anything for certain. It's also related to the problem of the criterion, discussed by philosophers like Roderick Chisholm in the 20th century. 2 ways to approach the paradox. Philosophers have proposed 2 main ways to tackle the problem, but neither is entirely satisfying. 1. Methodism. This approach says, let's start with a method or criterion for knowing things, and then use it to determine what we know. Problem. How do you know your method is reliable if you don't already know what's true? 2. Particularism. This approach says, let's start with particular things we know, and then figure out a criterion based on those. Problem. How do you know those particular things are true if you don't already have a criterion? Nar. Why does this matter? The paradox of the criterion isn't just an abstract philosophical puzzle. It has real-world implications. 1. Science. How do scientists decide which theories are true? They use methods like experimentation and observation, but how do they know those methods are reliable? 2. Everyday life. How do we decide what to believe? We use criteria like evidence and logic, but how do we know those criteria are valid? 3. Skepticism. The paradox feeds into skepticism, the idea that we can't really know anything for sure. If we can't establish a criterion for knowledge, maybe knowledge itself is an illusion. A thought experiment. Imagine you're trying to teach someone how to tell if a painting is beautiful. You might say, beautiful paintings are the ones that evoke strong emotions. But how do you know which emotions are the right ones to evoke? You'd need to already know what makes a painting beautiful to define beauty in the first place. It's a never-ending loop. Chakar, can we escape the paradox? Some philosophers think we can, but it's not easy. Here are a few ideas. 1. Pragmatism. Instead of worrying about absolute certainty, we can focus on what works in practice. If a criterion helps us achieve our goals, maybe that's good enough. 2. Coherentism. We can judge our beliefs based on how well they fit together as a whole, rather than trying to find a single, ultimate criterion. 3. Foundationalism. We can start with basic, self-evident truths, like I exist, and build our knowledge from there. Namarsha. Why is this paradox so frustrating? The paradox of the criterion is frustrating because it exposes the limits of human knowledge. It's like trying to see the back of your own head. You just can't do it, no matter how hard you try. But at the same time, it's also liberating. It reminds us that knowledge is a process, not a destination, and that it's okay to not have all the answers. Final thoughts. The paradox of the criterion is a humbling reminder of how complex and mysterious the world really is. It challenges us to think critically about how we know what we know, and to be open to the possibility that we might be wrong. So, the next time you're faced with a tough decision or a tricky problem, take a moment to wonder, how do I know what I know? And is that knowledge